Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element thorium. Although big chunks of thorium do exist, I don't personally own any chunks of the pure metal. So this video from Theodore Gray showing a strip of thorium metal is a nice substitute. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Thorium is the 90th element in the periodic table. Its atomic number is 90 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. While thorium has been around since the formation of the Earth, wherever you find uranium, you usually find thorium. Radioactive decay of the uranium causes both of the minerals you see here to contain thorium as well. More on this later. Uraninite, also known as pitchblende, is a radioactive, uranium-rich mineral and ore with a chemical composition that is largely UO2, or uranium dioxide, but because of oxidation, also typically contains variable proportions of U3O8, or triuranium octoxide. Carnotite is a potassium-uranium vanadate. You can see the uranium in their chemical formulae. Though these uranium-rich minerals contain thorium, there's too little thorium to mine them as a viable source. Berzelius was the first to privately claim the discovery of a new element he called thorium after analyzing a mineral called gadolinite, a rare earth silicate. He later retracted his claim. He was actually seeing the element yttrium, also present in another mineral he examined, xenotime, a yttrium orthophosphate. Both of these minerals contain several rare earth elements and often a smattering of actual thorium, but Berzelius was not seeing the thorium. Thorite is a rare thorium and uranium-bearing silicate mineral located in 1828 by Hans Morten Thrain Esmark, a Norwegian priest and amateur mineralogist. He sent a sample of thorite to his father, a professional mineralogist, who then sent the sample to our old friend Berzelius. This mineral is too rare to make it a primary source for thorium. This time, Berzelius determined that the mineral did indeed contain a new element. He reused his old name for this new element and called it thorium, after the Norse god Thor, god of lightning and thunder. Berzelius was also responsible for naming the mineral thorite. In 1898, 2 months before Marie Curie, Gerhard Schmidt, a German chemist, discovered that thorium is radioactive, the second element to be thus revealed. The most common source of thorium also supplies us with many of the lanthanide rare earth elements. The phosphate mineral monazite, which can contain up to 12% thorium phosphate, but usually 6 to 7% on the average. Extraction of thorium as a byproduct of rare earth element recovery from monazite seems to be the most feasible source of thorium production at this time. The first to produce actual metallic thorium in 1914 were Dutch chemists Lodewijk Hamburger and Dirk Levely Jr. Thorium is a member of the actinide series of elements, down at the bottom of the table. It's the second element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides are radioactive. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 90 protons for thorium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 32 known isotopes of thorium, and we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of thorium are radioactive. As we'll see in the next slide, most of the half-lives of thorium isotopes are fairly short, but there's a couple fairly long-lived ones in there too. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of thorium occupy the same place in the periodic table. Of the isotopes of thorium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest thorium half-life is thorium-232, with a half-life of 14 billion years, even longer than uranium-238 at 4.5 billion years. The most abundant of these isotopes is obviously thorium-232 with its extraordinarily long half-life of 3 times the age of the Earth and slightly longer than the age of the entire universe. Indeed, 4/5 of the thorium present during the formation of the Earth is still with us today. Thorium-232 accounts for 99.98% of the thorium found in nature. Thorium-230 accounts for virtually all the rest at 0.02%. The remaining isotopes occur only in trace amounts. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of dividing by 2. If we wait 1 half-life, half of your isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. 1 more half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If we waited 1 more half-life, our remaining atom would have a 50-50 chance of decaying in that time. Most of the thorium on Earth was there from the start, but some isotopes are from radioactive decay of other elements. Let's look at that. There are 4 important decay chains we'll look at. One starts with uranium-238, another with uranium-235, but it's actually called the actinium series to differentiate it from the U-238 series. Another that begins with neptunium, and lastly, the decay chain that starts with our long-lived thorium-232. Before we begin, I'm going to show you these series on a chart you'll see in many physics texts. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. Generally speaking, when an isotope decays, it can do this by emitting an alpha particle or a beta particle. And I'm oversimplifying this. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium atoms have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and the electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton, but does not change its atomic weight significantly, since electrons are so light. This time, we'll start with thorium-234. Gaining a proton, but not changing atomic weight, moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Now, let's look at a complete decay series. We'll start with the most common uranium isotope, uranium-238. Uranium-238 has a half-life of 4.5 billion years. I've listed the decay modes and half-lives at the top, but I'm not going to recite them anymore. Uranium-238 decays by alpha into thorium-234, one isotope of this month's element. Thorium-234 decays by beta. Remember, we move up 1 square for betas. And that decays into protactinium-234. That decays by beta into uranium-234. Note this uranium is a different isotope than the one we started out with. Uranium-234 decays by alpha into thorium-230. Again, a different isotope than the thorium before. Let's complete the decay chain. Thorium-230 decays by alpha into radium-226. Radium-226 decays by alpha into radon-222. Radon-222 decays by alpha into polonium-218. This very short-lived polonium-218 decays by alpha into lead-214. Lead-214 is a radioactive form of lead, which decays by beta to bismuth-214, which decays by beta into polonium-214, which almost immediately decays by alpha into lead-210, another radioactive form of lead, which decays by beta to bismuth-210, which decays by beta to polonium-210, our third isotope of polonium in this decay chain. This polonium finally decays by alpha into lead-206, which is stable and not radioactive. Quite a roller coaster ride from uranium to lead, passing through thorium twice along the way. Remember, our original uranium-238 had a half-life of 4.5 billion years. Since Earth is about 4.5 billion years old, about 1/2 of the uranium-238 on Earth has decayed to lead. Thorium has its own decay chain, starting with the most common and long-lived isotope, thorium-232. Again, I'm putting the isotope, its decay mode, and half-life up here in the yellow box for your reference. Our starter, thorium-232, decays by alpha to radium-228, which decays by beta, moving up 1 row, to actinium-228. This also decays by beta to thorium-228, a different isotope than we started with, and also different than the isotopes we saw in the uranium series. Thorium-238 decays by alpha to radium-224, again different than the previous radium isotope. This decays by alpha to radon-220, which decays by alpha to polonium-216, which also decays by alpha to lead-212. Lead-212 is a radioactive isotope of lead, which decays by beta to bismuth-212. Here, we hit a fork in the road. A little over 64% of the time, bismuth-212 decays by beta to polonium-212 with an extremely short half-life of 294 nanoseconds. That's 294 billionths of a second. This short-lived isotope then decays by alpha to lead-208, which is stable and not radioactive. But we need to return to our bismuth-212 fork in the road because a little under 36% of the time it decays by alpha to thallium-208, which decays by beta to our final destination, lead-208. Natural uranium is mostly uranium-238. A small portion, only 0.7%, 1 out of every 142 uranium atoms, is the isotope uranium-235, our starting point for this decay chain. This decay series is often called the actinium series so as not to confuse it with the uranium series which starts with uranium-238. I won't bother you with the details of this decay chain, but through a series of transmutations, the uranium-235 eventually decays to lead-207, which is non-radioactive and stable. Note, this series also produces 2 isotopes of thorium, also different from the previous 2 series. Lastly, we'll talk about the neptunium series. Here we obviously start with neptunium, the isotope 237, which is a natural byproduct of uranium decay and, more commonly, a product of fission in nuclear reactors. Again, I won't bother you with the details, but neptunium decays through thorium-229 to thallium-205, which is stable and not radioactive. This is the only decay chain we've seen so far that does not end in a stable lead isotope. In all 4 decay series, we've seen these 6 thorium isotopes: thorium-227, 229, 230, 231, 232, and 234. Since we're on our 7th radioactive element, 8 if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity and is one of the simplest things to measure. You can use a Geiger counter and just count the number of detections per second. But you need to take into account the size or area of the detector and its distance from the source, and multiply the measured counts per second as if your detector could completely surround and catch all of the disintegrations from every direction. The international unit for this is the becquerel, named after the discoverer of radioactivity, Henri Becquerel. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the Curie, obviously named after our dynamic duo, Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium, discovered by the Curies. Get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Now, radiation carries energy, and that energy is deposited in your body, or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milligrays or micrograys or something like that. In the US, we've used a unit of the rad, or Röntgen absorbed dose, which is 1/100th as large as the gray, but still a large amount of radiation. By the way, Röntgen discovered X-rays in 1895. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the rem, which stands for Röntgen Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are all human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer or genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem, per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th of the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to 10 millirem, and a chest CT scan gives you up to 800 millirems. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. The element thorium is fairly uncommon in the universe, coming in as the 76th most abundant element in the universe by mass at 4 parts per 10 billion. It's a bit more common in the Sun, but still only 3 parts per 10 billion. It's the 72nd most abundant element in meteorites at 3.9 parts per 100 million. Surprisingly common compared to everywhere else, in the crust of the Earth, it's the 42nd most common element at 6 parts per million, almost 3 times more common than tin at 2.2 parts per million. Thorium is the 89th most abundant element in the oceans, virtually non-existent at 4 parts per 100 trillion, mainly because it's almost insoluble in water. And lastly, like most of the elements in the upper reaches of the periodic table, there is no thorium in us except for the tiny bit absorbed from the environment. It's estimated there are about 6 million tons of available thorium, and as you can see, it's pretty evenly distributed. India has a good chunk at 14%, but that's only 1/7 of the total amount. As I just mentioned, it's estimated in the crust of the Earth there's around 6 million metric tons of thorium. Most is left over from the original formation of the Earth from the solar nebula. A negligible amount is created from the decay of other elements. If you could magically collect all the thorium from the entire Earth, you'd have a cube almost 84 meters or 275 feet on a side. Compared to a human, that's so large you can hardly see the 11-pixel-high human I just added. All these radioactive elements aren't just in the crust of the Earth. They're distributed through its volume as well, and in fact provide a substantial fraction of the heat energy that keeps the core and mantle hot. The four main isotopes providing the heat are potassium-40, uranium-235, and uranium-238, and of course, thorium-232, which makes up the largest fraction today, 44%. This wasn't always the case, however. Notice the half-lives of these isotopes are quite different. Potassium-40 has a half-life of 1.2 billion years, so decays a lot faster than thorium-232 with a 14 billion year half-life. Remember, the Earth was formed about 4.5 billion years ago. If we graph the decay of these isotopes, we see earlier on potassium was by far the largest source of heat, but has decayed away substantially to third place today. Likewise, uranium-235, with its 700 million year half-life, started out in second place, but has mostly decayed away to fourth place. Only about 1/2 of the original uranium-238 has decayed away, and now is the second highest provider of internal heat. And thorium-232, with its 14 billion year half-life, is still mostly around and accounts for most of the radioactive generated heat of the Earth. About 50% of the internal heat of our planet originates from radioactive decay. Heat flow from the interior to the surface of the Earth amounts to around 47 terawatts of energy, an impressive figure. Looks like thorium is common enough and doesn't have many applications, as we'll see, so it's actually pretty cheap. A kilogram of thorium will only cost around $300. Thorium has a density of 11.724 grams per cubic centimeter. It's a pretty dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds. You can see it's about the same density as lead at 11.34 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, thorium's density is 11.724 grams per cubic centimeter. Lead's just slightly less dense. If I wanted to add a cube of thorium to my collection, it would cost me around $630, but would probably raise a lot of questions if I tried to acquire 2.2 kilograms of radioactive thorium. I'll just use my lead block to substitute. Thorium has a melting point of 1,750 degrees Celsius or 3,182 degrees Fahrenheit. It has the 18th highest melting point, close to the top of our chart. Thorium boils at a blistering 4,820 degrees Celsius or 8,708 degrees Fahrenheit, giving it the 5th highest boiling point of all the elements. That's about 3,070 degrees Celsius above its melting point, giving it the second or third largest liquid temperature range of all the elements, depending on whose numbers you use. Quite impressive. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of the liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid only in a 2.51 degree Celsius range. Notice all the noble gases and hydrogen have very small liquid temperature ranges. Thorium has the third widest temperature range at 3,070 degrees Celsius. It's notable the next four elements of the actinides also have wide liquid temperature ranges: protactinium, uranium, neptunium, and plutonium. If we compare the size of the thorium atom to that of hydrogen, we'd see something like this, though I'm just estimating the atomic diameter since it hasn't been measured accurately yet. The thorium atom is about 4.7 times the size of hydrogen. Here's the electron structure of thorium. By the way, a picometer is a trillionth of a meter. Atoms are distinctly small. Looking at all the element sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. My estimated size of thorium places it in the upper region of the chart, maybe around the 13th largest atom, about the same size as some of the rare earth lanthanides above it. Not too surprising, since the actinides share many properties with the lanthanides above them in the periodic table. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of thorium. Let me enhance the contrast to bring out the specific colors excited thorium gives off. This is a very complicated spectrum with what looks like hundreds of colors from the reds through the violets. Spectra of the elements uniquely identifies them to scientists as each gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. This is a bit arcane, but relativistic interactions of the thorium electron's spin, motion, and interaction with the nucleus changes the electron energy levels within the atom, thus changing how its valence electrons interact with other atoms, hence subtly changing its chemical interactions. The relativistic effects also change its spectrum in subtle ways. These relativistic effects are more common near the bottom of the periodic table. Bet you didn't think relativity inside an atom made a difference. Aside from research, there aren't many current applications, though there are some interesting possibilities. Some of the applications of thorium used historically have been replaced with safer non-radioactive substitutes, but even the historical applications are interesting, if not laughable and/or scary. One of the most interesting uses of thorium may be in nuclear reactors, but it will take a bit of explanation. Nuclear reactors depend on elements that undergo fission. This means when a nucleus is hit with a neutron, that nucleus becomes unstable and breaks into two or more smaller nuclei with the release of two or more additional neutrons. A tremendous amount of energy in the form of kinetic energy of the fragments is also released. This is what generates the heat, which generates the power. The additional neutrons are now free to cause more atoms to fission. This exponentially growing number of splitting atoms is called a chain reaction. In this example, we used uranium-235 from the previous slide, but other isotopes of uranium and plutonium, among others, also have this quality. Those extra neutrons and their ability to create a chain reaction means that uranium and plutonium are useful in nuclear reactors if you can control the number of atoms fissioning, but in an uncontrolled chain reaction becomes a nuclear bomb. Uranium and plutonium's ability to participate and cause this chain reaction is because they're what's called a fissile material. Thorium is a bit different. If we start with the longest-lived isotope, thorium-232, when hit with a neutron, it becomes a different isotope, thorium-233, with a much shorter half-life, only 21.6 minutes. That decays by beta to protactinium-233 with a half-life of only 27 days. The protactinium-233 then decays by beta to uranium Uranium-233 with the fairly long half-life of almost 160,000 years. So far, there have been no fissions or neutrons that can cause further fissions. Uranium-233, however, like uranium-235, is susceptible to fission. If it absorbs a neutron, it can take place in chain reactions. Uranium-233 is fissile. Thorium, while not fissile, is susceptible to transmuting into another element that is fissile. Thorium is labeled as fertile. If you build your reactor core with fissile material surrounded by fertile material, you can breed more fissile material. These are called breeder reactors, and they can generate more fissile fuel than they consume. The experimental thorium breeder reactor here, the Shippingport Atomic Power Station in Pennsylvania, operated between 1957 and 1982. Here's the reactor pressure vessel, which contained the core during its construction. So we already have perfectly good reactors that use uranium and plutonium as fuel. Why should we even consider the large investment necessary to develop a new class of reactor? Thorium, as the feeder fuel in a breeder reactor, has some advantages over the typical reactor. But before I continue, let me apologize for using a bullet list in my presentation. Bullet lists should probably be outlawed by the Geneva Convention as a form of abusive torture, but here goes anyway. First, there's lots of thorium around. It's about 3 to 5 times as abundant as uranium. It's also easier to mine and extract, occurring in monazite sands and ores. Presently, thorium is a byproduct of rare earth element mining and production. Monazite sands contain a higher percentage of thorium than typical uranium ores. All the thorium found in nature is one isotope, thorium-232. So, unlike uranium, no isotope enrichment is necessary. Uranium in nature is mostly uranium-238, with only 0.7% uranium-235. To use this uranium in a reactor, the uranium-235 content must be at least 3 to 5%. The enrichment process is difficult and expensive. Thorium reactors would produce far less of the dangerous transuranic elements with long half-lives and the potential for use in nuclear weapons. As a matter of fact, a thorium breeder reactor would produce less than 1/100th and maybe 1/1000th the high-level waste of a uranium-plutonium reactor. Most of the thorium reactor byproducts will have shorter half-lives, meaning we only have to store the products for hundreds of years rather than the tens of thousands of years for a uranium-plutonium reactor. Though you still need some startup fissile material like uranium or plutonium, once started, this type of reactor makes its own fuel from the fertile thorium. You just need to keep feeding it thorium. Also, 1 ton of thorium can produce as much energy as 200 tons of uranium or 3,500,000 tons of coal. It's more efficient than a uranium reactor. The big drawback of a thorium reactor is that a commercial-grade, high-output thorium reactor has yet to be designed and built. There are many research projects out there working on the problem, but this won't be simple or cheap. Then again, clean fusion power has been 20 years away for my entire life and continues to be 20 years away from commercialization, so who knows? One of the earliest applications of thorium was to provide illumination. It was noticed that when heated, some elements give off more light, even though they're all at the same temperature. This quality is called emissivity. Karl Auer von Welsbach noticed this. He incorporated various elements into cloth mantles by soaking them in a liquid slurry. After drying, those mantles were then draped around a gas outlet pipe. After the cloth burned away, the remaining flame-proof ash mantle still contained the high emissivity element and glowed brightly even at lower temperatures. These are still known as Welsbach mantles, and you may find them in gas-powered camping lanterns. As a matter of fact, I have one of those mantles, and one of the elements Welsbach used was thorium, which is a high emissivity element. I have my Geiger counter here. Let's turn it on and listen. When I bring it close, you can see that this is quite radioactive. But let's get back to the slides. Nowadays, battery-powered white LED lanterns are rapidly replacing them, and for good reasons. You don't have to carry around flammable liquid fuel or propane gas canisters, and they don't give off noxious fumes, so you can use them in your tent without catching fire or suffocating. If you still want to use a gas lantern, present-day mantles use slightly less efficient but non-toxic and non-radioactive rare earths as the emissive material. Welsbach's invention was celebrated with a stamp in 1936, another in 1954, yet another in 2012, and a commemorative Austrian €25 Fascination Light coin in 2008. Oh, there's also a monument in Vienna. The plus lucis at the top of the monument translates to more light. How appropriate. Adding thorium to glass increases the bending or refractive power, leading to thinner and lighter lenses. This Canon 58mm lens contained some thorium. As I just mentioned, thorium increases the bending power or index of refraction of the glass. Whereas light entering normal glass, such as window glass, bends a certain amount, light entering thoriated glass bends more. For illustrative purposes, I've exaggerated the amount of bending for the thoriated glass. In reality, they only differ by 2.6 degrees, but the amount of bending for the window glass is correct. Second, dense thoriated glass makes better rainbows. This quality is called dispersion. So if you have a prism made from normal window glass, it produces a fairly narrow spectrum. A thoriated glass prism spreads out the colors more, making a wider spectrum. It's higher dispersion than the window glass prism. Prisms aren't normally made from thoriated glass for obvious reasons. Normally, lead glass is used for prisms, but that has its own toxic issues and is now a specialized item, if you can find it. I was just at an optics convention, and I couldn't find a single glass manufacturer that still makes thoriated glass. So I guess it's now a collector's item. Now you know some of the science behind Pink Floyd's Dark Side of the Moon album cover. They got the optics right. Unfortunately, thoriated glass, because of the mild radiation from the thorium, tends to yellow with age. This can be partially cured by exposing the lens to ultraviolet light for a period of time, though some photographers like taking advantage of the slight yellow tint of these lenses. Inside vacuum tubes is a glowing tungsten filament whose purpose is to boil off electrons used in the tube's circuitry. This is called thermionic emission. A bit of thorium, about 2% thorium oxide, is added to the tungsten filament, and this makes the electron emission more efficient. Likewise, thorium is added to tungsten electrodes used in TIG welding. TIG stands for tungsten inert gas because the melting and welding happens in a stream of argon or some similar gas. The thorium in these electrode rods makes the arc easier to strike and more stable. Also, the arc can carry more current, leading to faster welds. Let me show you some. Here are some thorium welding rods, and I'll bring my Geiger counter again into this, and we can see that the thorium rods are slightly radioactive. Thorium is only one element added to welding rods. Thoriated rods range from 0.8 to 2.2% thorium oxides. Because of the radioactive nature of thoriated rods, the non-radioactive rare earths lanthanum or cerium are often substituted for thorium, which works just about as well, without the worries from inhaling radioactive smoke. The most accurate clocks nowadays are atomic clocks. These depend on the transition of electrons between the energy levels of the atom. They're pretty accurate, 1 part in 10 to the 18th. This means the clock would gain or lose a maximum of 1 second in 40 billion years. Rather than using electron energy levels, energy transitions within the nucleus can improve this by a factor of 10. Using thorium-229 is proposed for such a clock. These clocks could lead to improved timekeeping and navigation, faster internet speeds, and advances in fundamental physics research. The discovery of radium created something of a sensation, maybe even a craze. Thorium wasn't far behind. Radioactive substances became a cure for just about anything that ailed you. What was a craze became quackery and snake oil. This doesn't quite qualify as quackery since it actually worked, but because of thorium's density, a thorium dioxide suspension called thorotrast was injected into approximately 10,000 patients to increase the contrast of heart, liver, and spinal cord x-rays. Needless to say, here the treatment was worse than the disease, and many of these patients went on to develop leukemia, liver, and bile duct cancers, as well as anemias and scarring of internal tissues. If radium and thorium can cure, why not bathe in the water enriched with the stuff, or even drink some? Here in Los Angeles, at the corner of Melrose and Gower, the present location of Paramount Studios, stood the Radium Sulfur Springs Hot Baths. It advertised, "Wanted, all sufferers from rheumatism, neuralgia, sciatica, colds, poor circulation, brights, eczema, stomach, kidney, liver, blood, nervous, and female troubles to get cured at Radium Sulfur Springs, Los Angeles by taking hot baths and drinking this natural, sparkling, foaming, radioactive mineral water. It is liquid sunshine. Physician in charge." Glad there was a physician in charge. If you couldn't make it to the baths, you could buy irradiated water. This one is certified, whatever that means. It contains both radium and mesothorium, whatever that is. Or you could make your own irradiated water at home, either with the rheode on the left or in a highly radioactive revigator like the one on the right. These were glazed with radioactive uranium ore, which contained a variety of radioactive isotopes, including thorium. Thoradia produced several products, including facial cream, allegedly containing radium and thorium. Of course, before you applied your cream, you'd want to wash your face with Salon Formula Thoradia soap. Here's their Thoradia face powder. It seems to have both radium and thorium as labeled ingredients. German dentists didn't want to be left behind. Here's Doramod, radioactive toothpaste. Its thorium content claims to be refreshing. Despite those historical quack products, thorium serves no biological purpose, so you'll find only a tiny bit within you absorbed from the environment, about 20 millionths of a gram. As usual, we'll end this talk with Mary Soonlee's elemental haiku about thorium. Electrons display relativistic effects in the table's depths. In the next program in this series, I'll examine protactinium, a relatively unknown element few people have even heard of. Still, I hope you'll join me. Just because it's unknown doesn't mean it's uninteresting. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element thorium.